Okay. First thing to do is to provide a little bit of a brief background on what the SN1 mechanism is and how that would affect the stereochemistry of different products. So let's go over that briefly. So if I have, for instance, a secondary halide like this, and I'm going to react it with something like water, which is a weak nucleophile. One of the things that we're going to find is that when you react a secondary halide with a weak nucleophile, and actually if you react a secondary halide or a tertiary halide with a weak nucleophile, the mechanism that you're going to get is SN1. And the reason for that is because weak nucleophiles can only react with carbocations. So if I'm looking at the mechanism of this reaction, I know that it's going to be SN1. So let me go through how we would write the mechanism of this reaction. And so we're going to start with having, and I'll put a dashed wedge here. I'll put the stereochemistry in. So we got a dashed wedge. I'll put a bold to the methyl group, and then the other bond in the plane to the bromine. So the first step of the mechanism is to break the carbon-bromine bond and give the pair of electrons to the carbon. Okay, when I do that, I'm going to form a carbocation. And that carbocation is going to have an sp2 hybridization. Okay, the bromine will go ahead and take the lone pairs with it. So in this sp2 hybridized carbon, there is a p orbital, but that p orbital is going to be empty. And so this is the first step of the mechanism. The second step then is for the water molecule to come in and add to the carbocation. And this carbon would have a plus charge then. Okay, so let me write out that carbocation down here. And these three groups have flattened themselves out so that it kind of looks like it's trigonal bipyramidal, except it's not. It's trigonal planar. So what will happen is that the carbocation has an empty p orbital with two lobes. And so the water molecule is going to come in and add to both sides of the carbon. It's going to add equally to those two lobes. There's nothing preventing it or making it want to add to one lobe over the other. So the first thing that's going to happen is my water molecule could add to the left lobe, or my water molecule could add to the right lobe. When it does that, it's going to form this oxonium ion. And now if it adds to the left lobe, then the ethyl group, the hydrogen, and the methyl group all end up on the right-hand side because the water is added to the left lobe. If the water adds to the right lobe, then I end up with my oxonium ion on the right side, and the ethyl, the hydrogen, and the methyl will all be on the right-hand side. Okay, now I didn't start with the stereochemistry of this, but I should if I looked at the stereochemistry of the initial molecule. Bromines 1, ethyl 2, methyl 3, hydrogen 4. 4 is pointing away from me counterclockwise, so I started with an S configuration. Okay. And over here, and let's just finish off the molecule, the mechanism here. So I form my oxonium ion, then my hydrogen-oxygen bond breaks and my pair of electrons goes back to the oxygen. So now I'm going to end up with, and each one of those oxygens still has a lone pair. So I'm going to end up now with this stereochemistry. And if I lose the H plus over here, then I'm going to end up with the lone pair having the lone pair going back to the oxygen, and I end up with this stereochemistry. So looking at these two, if I compare it to the original molecule, the OH is in the same place that the bromine started. So if I'm looking at this is group 1, group 2, group 3, and group 4. This is the S configuration, whereas over here, 1, 2, 3, and 4, that molecule is the R configuration. So when we do an SN1 reaction, we are always going to get a racemic mixture, which is going to be 50% R and 50% S. That's what we will always end up with. Okay, so that's how the stereochemistry is impacted or is produced in an SN1 mechanism.